Namaste. Welcome to tutorial series on process or bioprocess simulation using SuperPro Designer. In the previous two videos, we understood how to register pure components required for the citric acid fermentation simulation, and also as I already told, this particular process is divided into two sections. One is the upstream section, that is fermentation section, and the next section is isolation section. So in the previous video I understood how to develop the process flow sheet for this fermentation section, and we initiated all the streams and operations. Now let us simulate this particular process flow sheet and let us check what is the quantity of citric acid produced during the fermentation. To carry out the simulation, you have to click this calculator button. Let us solve this. Yes, there is one small error, that is stream on output P7 is used by store is currently missing. Okay, this is a small mistake where we forgot to connect this, as this was further need to be go to the next level of downstream, so I forgot to connect this. You can just connect this particular stream. We will, as of now, we will make it as a dead end, and also we can connect to one vent stream. So now let us simulate it. Yes, this particular error is disappeared. Now you can notice there are a lot of these boxes are appeared. The new symbol appeared. It shows that multiple units. So let us see that later, how to kind of reduce them, or how to remove this particular symbols, and what are these symbols. All these things we will look into it later. Now let us click on this particular stream to check what is the quantity of citric acid is produced. If you could notice here, in the total broth, it is around 15%, 15.35 mass percent is the citric acid, and you just click this metric ton, and you can notice there is almost 59.12 metric ton of citric acid is produced. So later, once the purification steps have been done, so we need to understand how much the total quantity of citric acid will be produced. So that is basically, there are a lot of losses in the downstream steps also taken into account. We should check what is the quantity of citric acid produced in the post downstream step. And also you want to check for each case any of the carbon source we had added, that is around something around 139.84 metric tons we added. And the water source, actually we don't know, because initially we added 100 metric ton of water to this reactor, and we used some quantity to purify to dilute the stream, dilute this particular molasses, and also we used water to prepare this particular nutrient. So if you go to this water source, you can understand, notice here, let us go with metric ton unit. 230 metric ton of water is consumed in this particular upstream section, or that is what we call fermentation section. Still there are a lot of sections where the water is also consumed, but basically from this particular source like around 230 metric ton is consumed. And also you can notice how much amount of regeneration buffer is basically used. If you go with metric ton, again it is 9.72, and that's what the steps we notice. That is, first the loaded, the particular molasses is loaded into the column, and also regeneration. Basically what happened, these impurities have been bound to this particular resin, so that need to be regenerated. That impurities are removed, and wash step, once impurities are removed, we have to wash the column to prepare for the further process. So and also you can notice this particular waste stream. So what and all during the regeneration and waste, like all these things come in this particular stream. And also you can notice here it does not contain any impurities, because this is like first step in the filtration step, we removed around 90% of the impurities. That's what you can notice here. Still some quantities of impurities are left. In this cake stream also we can understand that impurities and some quantities of other components are also appearing here. But finally, when you notice from the chromatographic column, so we don't see much of, we don't see any impurities, because we removed 100% impurities using this ion exchanger column. And also if you could able to notice how much quantity of this particular media, the nutrients have been drawn. If you just click on this particular stream, you can notice, that is, if you go to metric tons, around 27 metric tons per batch of these nutrients are used. And any of these carbon sources we added, that is 139 metric tons. But if you click on this, the post purification removal of impurities, it has come to around 347 metric ton, because adding water, all these things, it has become that much. And also, if you want to know the glucose concentration, you can just understand, double click on this one, you can notice glucose is approximately 20%. Initially in the molasses it was 50%, post dilution it has become 29%. So this is how we set up the fermentation step. And also, if you want to know what is the air consumed, if you click here, the air stream, I go to this metric ton, you can notice this is 1000 metric tons of air is drawn for this process. And the everything, air contains a nitrogen, oxygen as per our assumption as a stock mixture. And also, if you could notice here, still lot of content air is continuously come out, and still you can notice 991 means approximately 10 metric ton of oxygen might be consumed during the process. Even CO2 is one of the byproduct in the system. Based on that, if you calculate, approximately so much quantity of oxygen is consumed. So now let us proceed further and set up the downstream or like isolation step, and simulate it to understand how much purified citric acid can be produced. So I will just delete this particular stream as of now. Yes, and if you could go through the particular process flow sheet of isolation section, so whatever the fermentation broth is there, it is sent to the rotary vacuum filter. So now the reason is, the citric acid is an extracellular product. So our interest is in broth, not the biomass. So we need to remove the biomass. So we have to retain the broth or the liquid. So for that purpose, they have added one rotary vacuum filter. Rotary vacuum filter. Let us select this one, add it here. So from the rotary vacuum filter, so it has been sent to a neutralization tank where the precipitation of citric acid is taking place, reacting with the lime. So calcium citrate is formed, so that is precipitation is happening. So we need to have a neutralization procedure. This neutralization procedure is available in continuous reaction, and under the environmental reaction, stoichiometric, and we select this neutralization reaction. So we add one neutralization reaction, and once the neutralization is done, so we need to remove the calcium citrate. That is the reason further they have used one more rotary vacuum filter filtration. So rotary vacuum filter, select the rotary vacuum filtration unit. Once this is removed, calcium citrate is removed, that further this calcium citrate is sent to the neutralization tank, where this calcium citrate is converted into citric acid, and gypsum is one of the byproduct formed during the process. So we need one more neutralization step, the stoichiometric, environmental reaction, stoichiometric and neutralization. So we add one more neutralization step. So once the neutralization of this is done, so we need to remove the gypsum, and also we have to recover the citric acid. So that is the reason we need to have one more rotary vacuum filter filtration. We go to rotary vacuum filter, we place the rotary vacuum filter here. So once the citric acid is kind of that is available in the liquid is recovered, then it has been sent to the crystallization unit, where the citric acid crystallizes along with some evaporation process also. So let us go to unit procedure, phase change, and we can select continuous crystallization. This is a continuous crystallization. Once the crystallization is done, the crystals are removed again using a rotary vacuum filter. Let us go to this filtration, and rotary vacuum filter, we select one rotary vacuum filter here, and the final step is to remove the moisture in the citric acid crystal. For that purpose, rotary dryer is used. So rotary dryer, and we place it. Okay, so these are the steps in, are the equipments used in, procedures used in isolation step. And now I want to connect them. Here what happens, both are inputs, I cannot able to connect it. So let us flip this one, flip it, and this also let us flip it, and all these four equipments we can flip it so that it is easy to connect. Now we need to connect them. So what need to be connected, whatever the broth it is coming here, so that is the input now. So what is the input stream, you can see this is the default input stream. As I have already told, if you have any doubts regarding the input and output stream, we can just right click on this one, and there is a help command that will clearly shows what is the input and output, or else if you just place the cursor also, it can show you. You can notice here, if I place cursor here, it is telling it's a feed stream. We need to connect feed to this particular stream. And also we need to wash the cake. For that purpose, one wash stream is added here, wash stream is added, and we are going to get the cake, we are going to get this, this is the cake stream. You can notice here this is a cake stream and this is the liquid or our filtrate is coming out. So this we connect the cake here, cake stream, and for this further liquid whatever the broth is, because our interest is in broth, so this broth now we are connecting it to the neutralization unit. So we need to add one more stream to add the neutralization. If you click a cursor here, it is asking for us to add the neutralization agent. So let us add one stream for neutralization agent, and this particular stream is vent to our gas outlet. So this, let us connect this particular vent stream, and also this is now once it is neutralized, this particular complete neutralized stream is sent to this particular feed stream. This is the feed. Again water is added to wash the cake, and this is again a cake stream, this is cake stream. Now in this particular section, so we need to understand whether we are interested in cake or we need to retain the broth. In this case what happens here, the calcium citrate is precipitated, so it is a solid one, so that calcium citrate need to be recovered, and later stages it is again neutralized with sulfuric acid to convert into citric acid. So our interest is in cake, so let us send this cake stream into this particular neutralization unit. Please carefully understand, we are not interested in filtrate, we are interested in the cake. So now this filtrate we will just remove it, it is a waste now. Now again we need to add the neutralization neutralization agent. I select and add the neutralization agent here, and one more vent stream to release the gas, and now this particular whole mixture is again sent to this particular filtration system. Again water is used as a washing agent, and now again we are interested in the broth. Okay, now the gypsum whatever, because once the calcium citrate it dissolves in the liquid, now gypsum which is insoluble in the water is get removed. So now the cake is removed, so this particular whatever the broth we are going, or liquid filtrate we are going to get, that is sent to this crystallization unit. So during the crystallization evaporation is also carried out, so whatever the water vapors comes, that need to be sent continuously, and whatever the crystals you are going to get, that again need to send it to rotary vacuum filter. So we can add again water to wash the crystals, and now again we are interested in the cake, so we connect this cake to this particular drying equipment. So this is the default feed for the drying equipment, and further this is the waste from the rotary vacuum filter, and also this dryer as an output, that is the product, final product we are going to get. And also hot air need to be continuously supplied to this particular equipment, so we add one input air stream, and this is exit. So whatever the air which contains the water is coming out, also required one stream. So these are the procedures required, and also required streams we added. Let us rename this particular stream. So you can rename this as fermentation broth. Now this is a water, so already we have used water 1, water 2, so we will add water 3 here. This is the water 3 stream to wash it, and yes, water 3 is also available, so somewhere we have added water here. Yes, water 3 we have added here, so let us rename this as water 4. Click OK, and this is the biomass after filtration, biomass, and this is the filtrate which is obtained. Let us retain it, or we can rename it. And this is important, the neutralizing agent is the lime. Lime is the neutralizing agent. You can also write it 33% lime in the bracket. Click OK, and this is the vent stream. So already we have vent here, vent 1 is there, so let us rename it as vent 2. Click OK, and this one again we need to add the water for washing, that is water. Now this is 4 we added, we will add 5. Click OK, and this is the filtrate. Or we can name it as aqueous waste. Click OK, and this again we add sulfuric acid, that is H2SO4, and that is 10%. 10% H2SO4 we are adding. Click OK. And this is again vent stream. We rename it as vent 3. And this is where gypsum formation takes place. Again you use water. So now water 5 we have used. So we will use water 6. Click OK. And this is the gypsum. And here this is water vapor, and this one is the crystal. You can name it if you want. You can just have water here, one more water. This is water 7. Click OK. And again this is aqueous waste. We'll name it as 1 because already aqueous waste 1 is just aqueous waste is available. And you can name it as a hot air in, and this one will name it as hot air out. So now this is the final product, that is we will name it as Ca crystals. In a bracket you can write product. So these are the just few naming we have edited. And you can now we need to initiate some streams like input streams. Especially intermediate streams will be taken care during the simulation, but input streams we have to add. If you see the first rotary vacuum filter, so we need to add the water in this particular stream. We need to add the water, and we don't know how much water is required. Based on some criteria it will be drawn, so we'll just select it as auto adjust. Click auto adjust. Click OK. Next, in this particular stream, again we need to add the lime. Lime is again stock mixture, so we'll add the lime here. Again you can notice by default software is chosen as auto adjust. Based on the criteria it will try to choose this. Click OK. And the next here also we need to add the water, so select the water and auto adjust. Click OK. In this particular stream the sulfuric acid need to be added, that is again stock mixture. 10% sulfuric acid. Again you can notice software is selected as auto adjust. Click OK. And in this particular stream again we need to add the water and auto adjust. Click OK. And in this stream also we need to add the water, auto adjust, and click OK. And here we need to initiate the hot air. Conditions we'll see to it later. Let us just initiate the air in. Click OK. And anyhow the air out and Ca crystal post simulation it will be taken care. So these are the input streams we have initiated. Now let us initiate the add the operations and initiate the operations. Now in this case particular simulation of this downstream section, we need to set up stoichiometric equation at 2 places. One is here in this case where citric acid is converting it to calcium citrate, and in this case the calcium citrate is converting it to citric acid and gypsum. So that is the reason whenever as this both calcium citrate as well as the gypsum as newly registered compound, we went with some default properties of the already existing compound, so their molecular weights are not proper whenever you set up the stoichiometric equation. So what will happen if you are not adding proper molecular weight for the calcium citrate and gypsum, later you are going to face the error, or that imbalance will take place between the reactants and the product. That is the reason we need to set up the molecular weight. So let us go to this pure component register. Let us add calcium citrate. This calcium citrate, the molecular weight of calcium citrate now it is 192.15. I think it is like we registered along with as the properties of citric acid. We will change it, that is 498.46 is the molecular weight of calcium citrate. Click OK. And also we need to add the molecular weight of gypsum. So the gypsum molecular weight is, go to physical constant, it is 136 because we registered along with the properties of water. You can notice that 18 was there. Now we need to change it to 136. Click OK. Please do not forget to do these changes, because when you set up a stoichiometric equation you are going to face this problem. That is the reason it is important to change the molecular weight. Rest all properties we go with the default ones. If any changes required in the later changes, for example when you do economic calculation, we need to set up the prices. So that time, and also labor, all these things we will look into it later. As of now, for this particular section, like particular tutorial, what is required as of this particular step, isolation step, just I have changed the molecular weight. Click OK. So let us initiate this particular rotary vacuum filter. Now in this case, they've added one more operation to this one. By default, you can notice it's a continuous operation, a rotary vacuum filter. Continuously the broth is entering and it is getting filtered. They've added one more step called as hold step. They've added one more step called as hold step before this filtration step. That's the reason I've used this particular button to add it before the filtration unit. So what is this hold step? Is basically they have named it as apply pre-coat. Apply pre-coat. Apply pre-coat. So what is this basically? Pre-coat is in especially whenever you do the filtration, especially filtration or rotary vacuum filtration or any sort of filtration, biomass is highly viscous maybe many times, and it may not have a better filtration efficiency, any equipment. For that purpose you try to add some filter aids like diatomaceous earth and all these things. In this case also it is basically pre-coating, indicates that maybe that filter medium is kind of coated with this like any filtrate, so that the filtration can be efficiently happen. That is the reason they have added one more operation called as pre-coat. Click OK. Now let us go to this operation. Right click on this operation data, apply pre-coat. Now the pre-coat is applied for 60 minutes. So let us change it to 60 minutes, and the rest all we go with the default and go to the next operation, the filtration operation. Here the goal is to remove 100% biomass. So that is particular matter, that is 100% biomass need to be removed. And also you can notice here the filtration time. So filtration is carried out for 30 hours. So we need to set it as 30 hours. And the filtration rate, that is average filtration flux, we go with the 250 liter per meter square hour. And also the cake volume, the amount of wash stream. So now if you click this particular wash stream, we already added water, so that is available here. So how much wash the wash stream liquid is required, the quantity is required. Here it is by default chosen available in wash stream. If you click this, it will show you an error, because you can notice here we have clicked auto adjust, because based on some criteria it has to draw. So now as of now it is only 100 kg available. If it is exceeds 100 kg, then definitely it is an error. So now what is the purpose is like we need to set the volume per cake volume. So how much our cake is generated, based on that, so much quantity of water need to be added. The ratio is 0.6. Here initially it is 3, that is 3 volumes of water per cake volume. If 1 meter cube cake is there, we need to add 3 meter cube of water. So that is the reason now it is like 0.6. So 0.6 volume per volume of cake is added. The water is charged. Now next one more thing, here the loss on drying is assumed as 30%, and rest all we go with the default values, and there are no further operations. Click OK. Now let us go to this neutralization option. Again neutralization is a continuous phenomena, so already this operation is available. Click on this neutralize, and we need to add the exit temperature. Now the exit temperature is 50 degrees centigrade, and cooling agent we need to choose it as cooling water. Cooling water is used as a cooling agent. Now if you can notice here the neutralizing agent we already set up, that is lime and also auto adjust. We don't know the quantity, but is there any excess neutralizing agent is available to, because to enhance the conversion we can use excess neutralizing agent. That is in the, as per this problem statement, 5% excess neutralizing agent is available. And in this particular stream, because if the neutralizing agent is a complex mixture, what is the neutralizing component or agent? In this case calcium hydroxide, because it is only 33% calcium hydroxide. Water is also available. Water is not a neutralizing agent. Calcium hydroxide is a neutralizing agent. And also we go with all the other parameters with the default values. Here they have set specific power as 0.1. Basically when you do agitation, neutralizing process also requires agitation, they have assumed the specific power as 0.1 kilowatt per meter cube. So this is in operating condition. Next volumes, all these things we go with the default like values as of now. Next very important thing that we need to set up is a reaction. Let us go to the reaction, and we need to add the reaction here. So what is the reaction? So calcium hydroxide reacts with citric acid, gives you calcium citrate plus water. So you can notice the mass wise also it is 266, 516, it is not balanced. So we go with the molar ones. It is not 1 for all the side. Now it is 3 calcium hydroxide reacts with 2 citric acid and gives 1 calcium citrate and 6 water. You can notice here both the side it is 606.53, 606.55, approximately same. Click OK. So if you have not added the proper molecular weight of the calcium citrate, then it would have been with the property, because we registered calcium citrate as the properties of citric acid. Now it is 192, here 192. This particular it would have not been balanced. The reactant product quantity would have not been balanced. It become imbalanced, and definitely software will show you the error. Click OK. And one more thing they have given is 99.5% conversion for this equation, and also the reaction heat is given. So reaction heat with respect to calcium hydroxide, the component is calcium hydroxide, and the reaction is minus 1500 kilocalories per kg, and the reference temperature is 50 degree centigrade. So we have added all the details, and also in the volume section it's very important thing in continuous reaction system is like residence time. So how long you retain that particular streams, input streams in the reactor, so that the efficient reactions can happen. By default, if you notice, it is 0.5 hour and only 30 minutes it is left. It is not sufficient to carry out the neutralization, so it has been changed to 3 hour. And also vessel volume, what is the working vessel volume? It is considered as a 90% of the vessel volume. So rest all we go with the default values. Click OK. So what we did in this step, first we set up the operating conditions, then we set up the reaction. Before that we can even set up the volumes also, it is residence time and working volume, and we can set up the reaction with all the given details. So click OK. So now this particular reaction step is also done. Now we need to again go to the rotary vacuum filter. In this rotary vacuum filter again we need to add one more step called as pre-coat. I will not just I'll leave it as hold only. You can rename it as apply pre-coat. And now let us go to this apply pre-coat, that is hold operation. Now again pre-coat is applied for 60 minutes. Pre-coat is applied for 60 minutes, and go to the next operation is a filtrate operation. Now in this case, this particular calcium citrate, here in the calcium citrate is removed 98%. 98% calcium citrate is removed, and again filtration is carried out for 30 hours. 30 hours. Again volume of water required to wash the cake is 0.6, and lots on drying is 30%. So rest all the parameters we go with the default values. Click OK. Let us go to this neutralization. Now the calcium citrate is converted into calcium citric acid and gypsum. So let us go to this particular stream and add the operation. Again operating condition, this is the exit temperature is assumed at 35 degrees centigrade, and again cooling water is used. Cooling water is used for the cooling purpose, whatever the excess heat is generated. And you can notice already sulfuric acid 10% is available. We have initiated this, auto adjusted that one. So now the excess available is 4%. They have assumed it as 4%. Again in the stream, sulfuric acid is the neutralizing agent. So specific cover is again 0.5. So volume, basically whatever the residence time, same thing for this also, 3 hours residence time, and 90% is assumed. Let us go to this reaction. We need to add the reaction, add the stoichiometric equation. The reaction is calcium citrate reacts with sulfuric acid. Reacts with sulfuric acid, gives citric acid plus gypsum. So again you can notice it is imbalance. Again you can notice we have just changed this 136. If you are not changed, it would have been 18, because we registered as the default properties of water. Let us go to the molar, and 1 calcium citrate reacts with 3 mole of sulfuric acid and gives you 2 mole of calcium citrate and 3 moles of gypsum. So you can notice here both the sides 792 is balanced. Click OK. And also here the reaction is heat is given, and given the conversion is now it is 90% or like you can 99% conversion, 99.5% conversion. And also the reaction heat is given, so we will select this one, ignore, uncheck this one, and reaction heat is minus 750 kilocalories per kg, and the reference component is sulfuric acid, and the temperature is 35 degree centigrade. So this is what we have initiated all the steps. We initiated the volumes also. Click OK. So this particular neutralization step is also done. So now we need to remove the gypsum because any of calcium citrate is soluble in water. Let us go to operation data. And yes, we forgot to add one more step called as pre-coating. Let us go and add one old operation before this filtration, that is pre-coating. Let us go to this particular operation, old operation, that is pre-coating. Basically you can rename it, as I already told, minutes. We can pre-coat it for 60 minutes and go to the next operation. So here in this case, filtration, we assume that this particular citric acid loss is 1% citric acid loss, and the gypsum is removed 95%. Gypsum is removed, and again filtration is carried out for 30 hours. With default flux, and the cake water required to wash the cake is 0.6 volume per volume of cake, and loss on drying is 30%. So rest all we go with the default value. Click OK. So now in the continuous crystallization, let us go to the as is. Again this is a continuous phenomena, already operation is available, you no need to add it. First step is we need to set up the operating condition. Specific power here assumed is 0.1, and residence time, so how long it stays there, it is assumed as 6 hours. So let us click this hour and select it as 6 hours, and rest all setup time is 0. And the process time, basically this residence time or process time, it is 6 hours here, 6 hours. So now evaporation data. So volume, we just assume here basically the residence time for this particular one, as it is a continuous process. Previously just assumed that as 6 hours. The process time is also 6 hours. Same thing, like we can see this residence time, we can set it as 6 hours, and 90% reactor is utilized. And we go to evaporation. So what need to evaporate? Once it you are filtered, basically this particular whatever the filtrate coming out of this system contains this gypsum, some quantity of gypsum, because 95% is only removed in the filtration step. Some gypsum might be there, and also you can have the complete citric acid is dissolved in the water. So in this first they are evaporating the water, means they are concentrating before crystallization to create the saturated solution. So water is evaporated. Let us go to this water and select. We are not able to edit this, so that is the reason we have to check this first, perform evaporation prior to crystallization, and in this case the 50% water is evaporated. Then the evaporation temperature is 100 degrees centigrade, and also all this evaporation heat, all these things we go with the default value. So what is the reference component during this process is the water. So we need to select water as a reference component. So we need to, because that is what evaporation overall process is depend upon this particular water, means in the sense evaporation step the goal is to remove this particular water, that is the reference component. Next one we go with crystal data. So what is the crystal form, which one is available as a crystal form? So now it is like a Ca crystal. So whatever the particular citric acid is available, whatever the citric acid is there, that is a component is obtained as a crystal form. That is nothing but, here we can go and add it as a crystallized form, Ca crystal. This Ca crystal citric acid is now kind of converted into Ca crystal. That is what you can notice, crystal form. So all these values we go with default values, and also the component is the citric acid, is the design component is citric acid, and you can notice the yield according to the problem statement is 98% is yield, and crystallization temperature is 15 degrees centigrade, and chilled water is used as a cooling agent. This is what the setup of the overall crystallization is. I hope you understood this particular operating condition. We have just the process time is set as 6 hours, and in this volume how long this liquid stays in the crystallization unit is 6 hours the residence time, and working volume is 90%. Evaporation data, prior to crystallization the water is removed to concentrate the filtrate obtained from the rotary vacuum filter, that is 50% water is removed, and heating temperature is 100 degrees centigrade, and all these parameters are default, like evaporation heat is default, the reference component is water. So based on this your evaporation is taking place. Steam is used for evaporation, and the crystal data, here the citric acid is converting it to citric acid crystals, and citric acid is the design component, and also the 98% is the yield of crystallization, and rest all we go with the default crystallization heat and all we will just retain as such, and we go to the next step, that is click OK. And in this case the rotary vacuum filter, again we need to add one more step of pre-coating. Let us add this old before this pre-coating. Let us go to this particular hold operation, and it is 60 minutes pre-coating again. And let us go to this next step of this filtration, that is rotary filter. In this filter again it is carried out for 30 hour, filtration is carried out for 30 hour. Rest all we go with the default value, it is also 0.6. And Ca crystals, here in this case Ca crystals are removed 98%. 98% Ca crystals are removed. This loss on drying we set it as 30%. So rest all we go with the default values, click OK. So we need to set up the this one particular air stream. Let us go to the rotary dryer. We can go back to this operating data. Again it is a continuous phenomena. We can set it up here. The basically water is removed, that is water. We can go here and select water, and we removed around see, you can notice calculate based on final set by user. Into set by user it is 98.81%, 98.81%. And relative volume, so we need to set it like relative volume of this particular one, flow of this particular air. Drying gas is hot air, you can notice here drying gas is hot air, click OK. And what is the quantity, at what rate you are sending, the relative volume is chosen. The relative volume is 1, so 1 like weight of gas per weight of evaporation. Based on that relative volume, 1 is set here. And you can also set evaporation specific rate as 20, we go with default values. And also here very important thing is outlet gas temperature, that is 110 degree centigrade, and the drying product also 110 degree centigrade. So and again all these things are okay. You need to set up the utility data. Here in this utility data, the specific power assumed is 0.6, specific power assumed is 0.6. So rest all we go with the default. In the operating condition also, just based on the loss on drying it is calculated, that is set up all, click OK. So everything we have set up, click OK. So basically we set up all the streams and operation in the downstream step. And let us now simulate this. Now it is, the process is complete, it contains both upstream as well as downstream section. So we added all the operation. Let us see any errors in the process now. So click the calculator symbol. Yes, is going on. Yes, ended successfully, there are no errors. If you could able to open, or if you open this particular section, you can notice, click the metric ton, the 54.54 metric tons of 99.49% purity citric acid or citric acid crystals are obtained in this particular stream. And also you can notice how much gypsum is produced. You can just click on this metric ton. So that is almost 57 again metric ton of gypsum is produced. Same quantity citric acid, same quantity of gypsum is also produced. This is the problematic actually in citric acid production. When we use lime for a purification purpose, lot of this gypsum waste is generated. That is the reason people try to go with nowadays other form of purification steps like solvent extraction or different methodology people are trying to employ. And if you want to understand how much air is sucked in this process, almost if you also check in metric tons, almost 22 metric ton of air is used to drying. And also if you notice how much sulfuric acid is used in the metric tons, so you can notice 456 metric ton of sulfuric acid is used for neutralization step. And lime also, if you could able to see, almost 108 metric ton is consumed. And also biomass, if you notice, almost 6 metric ton of biomass is produced in this particular process. And this biomass could be used for any other purpose. For example, this could be used as an animal feed after processing, or you can extract other components in the biomass. Maybe citric acid like Aspergillus niger also as a fungi can also produce some other valuable components which is available inside the cell. Maybe this could be again recovered, and whether it will be used as an animal feed or a food purpose, that is the later condition. Later we need to check all those steps. But as of biomass, it contains many other molecules, secondary metabolites that could be recovered and utilized. That will again enhances the process economics. In the sense, it will also value addition to your profitability. So basically this is what the process like upstream and downstream step. And in the next step let us understand how to kind of do the debottlenecking analysis. We have not scheduled many operations. We went all with the default values. We have not scheduled the process in many cases. Let us schedule these operations in the next step, and let us perform the debottlenecking analysis, economic analysis, and try to understand better the process simulation. I hope you understand how to simulate a little complex process in Citric, like complex process in bioprocess or chemical process industries. If you properly understand this particular simulation, I think you can set up any kind of process and simulate it. Basically, that may you need to use it for your academic project purpose, or you can use this simulation effectively for your research studies also. Because most of the time in laboratory condition we cannot able to evaluate what happens in an industrial scale, because we generate lot of laboratory data. That laboratory data could be fed into this software, and we can predict what could happen in industrial scale, because most of the research end up in lab scale and research and as a one publication. But yes, being an engineers, we can understand better what happens in the process condition. Thank you for watching. Please do not forget to subscribe.